Hello everyone, welcome to our calculus course for this semester. Today I'm going to cover 3 sections of chapter 6 from 6.1 all the way to 6.3. So let's start with section 6.1. It is about how to calculate the area. Okay, so let's recall the definition of integral is a fundamental theorem of calculus, I think. The x-axis, y-axis, and a definite integral. This is function f of x. For the uses of our first example, let's start with f of x above the curve, right? And what we learned in chapter 5 last week was what if you want to calculate the area of the region bounded by the function f of x, which is above the curve, bounded by the x-axis and the 2 vertical lines, say from x equal to a to x equal to b, and that was defined in calculus was what the area is equal to integral from a to b for the definite integral of f of x dx. And the idea for this is what? The idea to calculate this area is we're going to chop this region up into many vertical bars. Okay? And if the thickness of the bar is close enough, right, then the height is just like f of x. Kind of idea like this, and then the thickness is say delta x, okay, and the height is say f of x, okay, as a function. And if you chop it to many little bars, another word, take n go to infinity, where n is a number of the bars that we have all over the place. We chop it up to many bars, okay. All right, then we have the integral, and dx now, delta x now becomes dx. So you think what this is? Think of it as like the height times the width. This is the area of one little bar. You sum up all of those, run from A to B. This is going to give us the area. Okay, and by the way, sum them up, it's called the Riemann sum. Okay, that was a review that we got from last time, which is from calculus 1. Now we're going to calculate the physical area. Means what? Sometimes the graph, the picture may not be that nice. Okay, what if you have a function f is like this. This is my f of x. And then this is a. And this is b. If you do integral from a to b, f of x dx, say the intersection right here is c, then integral from a to c is going to give you a positive answer. But the integral from c to b is going to give you a negative answer because the height right here for f of x is going to be a positive number. But from c to b, f of x becomes a negative number. So if you really want to calculate the area all the way from a to b, you have to break it up into 2 different integrals. You have to calculate the integral from a to c f of x dx, and then you have to calculate the integral from c to b f of x dx, and this is a negative answer. Okay, so instead of adding, you do a subtraction. I mean, what? You flip the area from below the x-axis back to up above the x-axis, and then you're going to have the area from all the way from A to B. Okay, so it's not really a new thing. What's in here, we're talking about the physical area, not integral from A to B. Yeah, give you the function f of x right here. Ask you to find the area there, enclosed by the curve, the x-axis, and the 2 vertical lines, x equal to a, x equal to b. So anything that is above the x-axis, you do as normal. Anything that below the x-axis, you put a negative sign in front. Then, because f of x dx is a negative number, you put a negative sign in front, you will have a positive area. Now it's really a physical area. Okay? And then let me give you another case as you may have before I give you examples. Okay. Now instead of having 1 functions, what if you have 2? Okay, this is your f of x, okay? And this is your g of x, and then they ask you to calculate the area bounded by 2 functions f of x and g of x run from a to b. Okay? So here's the idea. If you calculate the integral from a to b f of x dx, you're going to have this area. Right? The area that is above the x-axis, below the function f, and bounded by a, x equal to a, x equal to b. Okay? And then if you calculate the integral from a to b of g of x dx, you will get this area. The area area bounded by the x-axis, the function g, and of course x equals to a to b. So if you want to calculate this difference, this area a right here, all you have to do is take the integral from a to b of f of x, subtract the integral from a to b of g of x. Okay, so in short, you can do it this way: integral from a to b of f of x minus g of x dx. Then you have the area in between. Okay. Last case before I can give you an example. So I have this. What if my function f is like this, and then my function g is like this? Okay, and they ask you to find the area enclosed by the function f, function g, and x equal to a to x equal to b. Okay, so you see what? The function f intersect, the graph of the function f intersect the function g at a point. Let's call it C. So from A to C, f is above, g is below, right? You take the above one, subtract the below one, right? Okay. But for the second part of the graph, what happened in here? G is above and f is below. And very similar to the idea of just a single function f that I showed you before. You want to calculate the total area of the two parts. You have to split the two, right? The first part, integral from A to C. F is right here, G is down here, so you do what? F of x minus G of x dx, okay? And then the area from C to B, now you take what? G of x minus f of x, right? G of x minus f of x dx, and you add the two areas together. Okay? Or if you want to write subtract right here, you go to f minus g. Okay? But this is what it means. When you have f is above, then take the above f, subtract the g. Okay? You have the physical area, positive number. And in here, when you have g is above, then you do what? G minus f, the bigger one, subtract the smaller one, an integral. Okay? Then you have the positive number again. You add them up, you have the total area. Okay, so that is the whole idea of section 6.1, and I claim that the integral part is going to be the same as what you learned in chapter 5. So let me just give you a general example that covers all the things that we just learned. Okay, how about one that got both cases? Maybe a couple of examples. Give the function y equal to cosine of x. Okay. Then let me try to show you guys a graph of it. It looked like this. It just make restriction from 0 less than equal to x less than equal to. This is x equal to pi over 2 and y equals 0. Right? This is a function cosine. This is y equal to cosine of x. And if I ask you to calculate this area, okay, this is 0 right here. When x equal to pi over 2, cosine of pi over 2 is going to be 0. And if I ask you to calculate the area bounded by the function y equal to cosine of x, and the y-axis and the x-axis right here, this is my y-axis, this is the x-axis, then what? This area will be equal to the integral x run from 0 to pi over 2, right? And the function is cosine of x dx, and I bet this integral is super easy for you guys to work with, so I'm going to leave it for you. What is the integral of cosine? Sine, right? Sine x, and run from 0 to pi over 2. You plug in x equal to pi over 2, sine of pi over 2 is 1. Sine of 0 is 0, so the answer is 1. Yeah. Okay? Good? Now, what if I give you another function? Say y equal to sine of x. Okay, so two functions. Again, x still run from 0 to pi over 2. This one is y equal to cosine of x. Okay. Let me use a different color and draw another function. Y equal to sine x. And the graph going to be like this. Okay, this is pi over 2, and this is pi. Okay. Can you find the intersection between the cosine and sine function? You set cosine equal to sine. Cosine of x equal to sine x, and then you solve for this. I can divide both sides by cosine of x, and it's not 0, so 1 equal to tangent of x. What value make tangent equal to 1? X is pi over 4. Right here, pi over 4, right in the middle. Okay. So, what if I want you to calculate this area? The green one right here. So you have to take the upper function, subtract the lower function. The upper one is cosine, the lower one is sine. And x run from 0 to pi over 4. So this green area will be integral from 0 to pi over 4. What upper one is what cosine of x. Cosine is a black one, and then the lower one is sine of x. This is sine, okay? Y equal to sine of x, the red one, minus sine of x, everything dx, and of course you can integrate it easily. That was the idea. Okay, now what if I want you to calculate the area bounded by the two functions, cosine and sine, but instead of from 0 to pi over 4, what if I ask you to calculate the area when x run from 0 to pi over 2? This is pi over 2 right here. Now you see that we have two regions, right? The first one is the green one right here, and the second part is the green section right here, bounded by two curves. The area bounded by cosine function and the sine function when x run from 0 to pi over 2, from here to here. Okay? So you see what? The first part, cosine is on top, sine on the bottom. The second part, sine is on top, cosine on the bottom. So we're going to have two integral. The green area is going to be what? The first part is integral from 0. This one is pi over 4. I think we have that before. Take the upper one, subtract the lower one, which is what? Cosine of x minus sine x dx. And of course you can integrate that. Integral cosine is sine, integral of negative sine is cosine again, so sine minus cosine, pi over 4 to 0. And then the second part is what? The integral. Now the sine one is on top, so sine x minus cosine x dx, okay? But the integral is not from 0 to pi over 4 anymore. It's going to be pi over 4 all the way to pi over 2, and you have the answer. So it seemed like easy when our book write the formula this way. The area is equal to integral from a to b, absolute value of f of x minus g of x dx. And this is just write one, but actually when you guys really have to do the math, you just can't work with the absolute value directly. You have to break it out. Okay, you take the upper one, subtract the lower one, so maybe from a to c, and then from c to b is g minus f. This is how our book writes. It doesn't matter, you still have to break it out. Graph is a very useful tool to see the intersection, and then take the upper one, subtract the lower one. Make sure that you have positive area. Okay? So I would not subtract. I would not suggest this write in the formula this way, even though it looks compact and it's easy to write just one formula. But I just unpack the whole package for you, and then you can do the math really with those kind of things. Okay, and that was 6.1, and I gave you this example, and I think that's easy enough for you guys to integrate, so I did not do it for you, but I'll do some other example later on. But this one should not be hard for now. And of course, even though I say that, if you really have problem integrate this thing, please take a look at some examples, or just shoot me an email, and then I'll show you how to integrate those. Okay, I think it shouldn't be a problem with a Cal 2 student. Next, I'm going to talk about section 6.2. I'll be talking about a volume of revolution. Okay? Volumes. And as well as 6.3, we also talk about volumes. In the old days, we call it the dish method or the washer method, and in here just so, very fancy word called volume of revolution. So let me just use the old way, okay? The disk method. That's for the washer method. What is it all about? So I think let me start this with a general case, and then I'll show you example right away, and make sure that you all get it. Say you have a function. This is f of x. We're only restricted from a to b. Okay. Now imagine that we are rotating that function f about the x-axis. Keep rotating. We are rotating the function f about the x-axis. Okay. So what we see is this. Let me use a different color, make it stand out. Rotating about the x-axis. So we have something like this. Hopefully you can imagine that. Okay. Function f rotating about the x-axis. So we have a 3D object. And the question asks us to calculate the volume of that object, of that solid thing, when x run from a to b. That portion only. Okay? So in general, the idea of calculus is whenever you want to calculate a big thing, what do? We chop it down into very little tiny things, and then we calculate the quantity of that little tiny thing, one little tiny thing at a time, and then we add them up. Okay? Same idea in here. So we want to calculate the volume of that solid, right? So imagine if we chop it up into many discs, many little discs. Okay? So this is a disc. Let me draw it on this side. This look like this. Okay? That little disc. Let me draw it in a vertical way so it looks like this one. It's easier for you to see. Okay, you guys see a dish? Okay, that's what it calls the dish method. And we're going to calculate the volume of that dish, okay? And imagine that we chop it up into many little dishes from all the way, when x run from A all the way to B. And then you add the volume of all the little dishes together, and we have the volume of the entire object. So one dish, how do we calculate the volume? The volume is the area times the thickness, is that right? We chop it out, the thickness is dx, okay? Delta x, but go to infinity is dx. And the area is what? Area of a circle. This is the radius called r. So the volume of 1 liter disc, I call dv, liter volume, is the area of a circle is pi r squared times the thickness, all right? Dx in this case. So what is the radius here? Well, it's obvious that the radius here, if you take n go to infinity, the disc, the slice is very small, and the radius is just f. Okay. In this case, r is equal to f. So the little volume is pi f of x squared and then dx. Now you want to add all the volume together. V is the sum of all the little v. Okay. This notation is just really what I'm adding all the area of all the little volume together, which is how to make it again. The integral from a to b. Pi is a constant. It's okay for me to bring it outside. So f of x squared dx. And this is going to be the volume of the solid region when you rotate the function f around the x-axis when x runs from a to b. Make sense? Okay, so actually this is the formula in the book, and this is my square thing. And you guys see why it's because of this method? Because what? When you chop it up, one slide looks like a dish. Okay. So this is the idea. This is the most important part, guys. Make sure that you get the idea, and you guys can figure out the formula by yourself. Now, let me show you another problem. X-axis right here, the y-axis right here. This is my function f of x, and this is my function g of x. Okay, and they imagine one more time. We're gonna rotate not just one function. Okay, two functions about the x-axis, and then calculate the volume enclosed by the two for the solid region enclosed by the two function. Right, so if I rotate around, this is my f again, and this is my g. Okay. All right. Yeah. Imagine that you're rotating around. So let me draw it right here. A big circle, smaller circle. Okay. Both ways. All right. And the idea is exactly the same. What do? We chop it off, right? So subtraction, that's the key, right? We calculate the entire volume enclosed by the f function and the x-axis, and then we subtract the volume, the core right here, enclosed by the g function and the x-axis, then you have the answer. So the volume now is what? Integral dv is minus integral from a to b of g of x squared dx. Okay? Right? So in short, we can write this way. V is equal to, take the pi outside, integral from a to b, f squared minus g squared, and the f squared means f of x squared, and then g squared means g of x squared dx. It's just really two volume. The volume of the entire big thing divided by f, and the x-axis, the whole apple right here. And then the second pi subtraction right here is the volume of the core, g of x, and the x-axis right here. You rotate, you have the core. You take the entire apple, subtract the core, you have the part that we can eat. Okay? And this is the more general formula that you have two functions. Okay, now let's talk about a more general case. What if I don't want to rotate about the x-axis? What if I just want to rotate around a random horizontal line? Draw one more time. This is my function f of x. Okay? X-axis right here, y-axis right here. What if this time I don't want to rotate about the x-axis? Instead, I want to rotate about this line right here. Say y equal to a, whatever it is. Okay? So I am rotating about this line. All right, keep in mind. So if I rotate, I'm going to have rotation f right here. The center is right here. Okay. The axis of rotation is y equal to a, not the x-axis anymore. And of course, the idea is the same. You chop it out into many little slices. Now let's do a dish, right? And then you calculate the volume of that little dish. dv is pi r squared times dx, because you chop it out this way, dx. But the radius is the thing that we have to be careful. It is not the distance from the x-axis to the function anymore. The radius is from here to here. Okay? From here to here. So the radius now is calculated this way. Radius is equal to f of x minus a. F of x minus, what does it mean by that? This is the function f, but the distance from f to a, you take f minus a, you have the distance. Okay, this is the radius. So dv now is pi of f of x minus a, everything squared, dx. Okay? So the entire volume will be, pi is a constant, you bring it outside, integral of f of x minus a squared dx, and oh boy, I should not use a here. Okay, that's a. So the integral gonna run from, say, x equal to alpha to beta, whatever, or c to d, because I use a here already. For example, what if I got y, it's a half example, okay? Y equal to -2. Okay? So this is the distance from the function to the x-axis. And the distance from here to here is 2, right? So the radius is not f of x anymore. It's going to be minus negative 2, because a is negative 2, which is f of x plus 2. This is plus 2 plus 2, and you have the formula. Okay. I forgot to explain to you why we have the name of Washer method. Recall that we have two functions. This is f of x, this is g of x, right? And you chop it up into one slide.